Chapter 14, Vibrations and Waves. Section 1 is about periodic motion. So what is periodic motion? Periodic motion is any motion that's going to repeat in a regular cycle or at a regular time interval. So we have what's called the period, and that's capital T. It's a lot like time. It's measured in seconds. But we're using capital T instead of a lowercase t. And the reason is because period represents the time needed for an object to repeat one complete cycle of motion. Okay, so one complete cycle of motion to occur here. So it's not necessarily the entire time or the average time taken, but just one complete cycle. So think about a bicycle or even the tire of your vehicle. The time that it takes for that to go around one complete time, that would be the period. We also have what's called amplitude. That's the maximum distance that the object moves from its equilibrium point. So, for example, if you have an object that is on a rubber band or attached to a string and you pull it away from that, the maximum distance you could pull it away from its resting position would be the amplitude. So the first formula that you're going to learn for today is Hooke's law. It's when we're talking about a spring that exerts a force, and that force has to be directly proportional to the distance that that spring can be stretched. So we're talking about metal springs here, and we have F equals negative K times X, or negative KD. So F is our force, that's always going to be measured in newtons. K is our spring constant, that's going to be in Newton meters or Nm. And that is going to be a number that stays with you depending on the spring that you have. And X or D is your distance of stretch or compression. So it can be either pushed in or pulled out for this. And that is in meters. Now, springs do have energy, and we're going to talk about the potential energy of that. So the potential energy in a spring is half of K multiplied by X squared. So potential energy in a spring, that's in joules. Okay, your spring constant, that is in Newton meters. And then your distance, X, okay, that should be in meters. So this is a lot like the formula for kinetic energy, only instead of having mass times velocity, you have spring constant times distance. Okay. So looking at an example, we have a spring that stretches by 18 centimeters when it has a bag of potatoes weighing 56 newtons suspended from the end of it. And I want you to determine the spring constant. So first thing you need to do is convert 18 centimeters into meters. So you should get 0.18. And then you have newtons is your force. So 56 is your newtons. Okay. Now it says determine the spring constant. So the formula you're actually going to use is F equals negative KX. Okay. So F is 56. That should be equal to negative K multiplied by 0.18. So when you plug in, and you'll need to rearrange so that you can solve for negative K. And again, it is a negative that's plugged in there. So be careful. So you get 56 divided by 0.18. That gets it moved to the other side. You should get roughly about 311. And that should be your spring constant for this one. Okay. There are some practice problems that I want you to do, so you can go ahead and stop the video now, or you can wait until the end. Just make sure you leave enough space for problems 1 through 4 on page 915. Jumping on, last thing for this section is when forces are applied to a vibrating or an oscillating object at time intervals that are equal to the period. Okay, so you have a force that's applied, it's applied to an object, and it's applied at time intervals that equals the period. That's when you get something called resonance. And if you want to look more into that, you can look at page 920 of your iBook at the end of this video. Let's go ahead and jump on to section 2, so we're not wasting any time here. Wave properties. So these are things that you will find that is true of all waves and wave behavior. So exactly what is a wave? It's a disturbance that carries energy through matter or space without transferring the matter. Okay, so it's something that moves through any object or almost any object, but it doesn't make that object itself move. Okay, So we have three types. The first type is a transverse wave. It's a disturbance of the particles that's perpendicular to the direction of travel. So if you think about moving forward, this direction of travel is going to be up and down. Okay, so think about taking a picnic blanket and you want to get all the ants off of it, so you're shaking it up and down, right? We also have longitudinal waves. These are disturbances that are parallel to the direction of the wave's travel. So if you have a slinky on a table, you are pushing and pulling that slinky back and forth. It's not moving up and down, it's just moving with the direction of travel. So it's compressing and then spreading out again. Surface waves is the third type, and that's where your particles follow a circular path. So think about ocean waves. They kind of move in that circular motion. If you've ever seen a buoy out in the middle or out in the ocean where it marks the continental shelf, you see that they stay stationary. They're moving up and down, but they're not getting closer or farther out to shore. The next thing we're going to talk about is the crest. It's the high point on a transverse wave. So again, this is the one that's moving up and down. Okay, so it's the high point, or what we would call the hilltop. Okay, and we also have the trough, which is the low point on a transverse wave. That's the bottom portion, or what we would call a valley. Wavelength is another important aspect. It's the space between two crests or between two troughs. It's represented by the Greek letter lambda. And wavelength is a length, so it's still measured in meters. But when we get to a formula in just a few minutes, you'll see lambda is going to be very important. The other important part is frequency. It's the number of complete oscillations that a wave can make in 1 second. So it's very similar to the period, only this is the number of oscillations in 1 second, okay? Whereas period is how many cycles it can complete, is how many seconds it takes to complete just one of those cycles. Frequency is measured in hertz, so Hz is how we're going to represent that, and the H should be capitalized. And this is how you can find it. So just like I was talking about with period, it's similar, but it's not quite the same. So frequency is equal to 1 over the period. We could switch that around. We could also say that the period is equal to 1 over the frequency. So when you get your assignment for wave velocity, don't forget to come back to this formula. It's going to be important in order to help you figure those out. Now, I will go ahead and tell you on your reference packet for these problems, you will find a section. It should be on the 3rd or maybe the 4th page. It will say waves. That's where you're going to find all your information for wave velocity and wave behavior. So how do we find wavelength? Lambda is equal to velocity over frequency, or we can write it as V equals F lambda. So lambda, that's your wavelength in meters. V is your velocity in meters per second. And then frequency is F, that's your hertz in capital H, lowercase c. So let's do a couple of example problems. We have a sound wave that has a frequency of 192 hertz. And it travels the length of a football field, which is 91.4 meters, in 0.271 seconds. I want to know, what is the speed of the wave? Well, in this case, because it doesn't tell you what the wavelength is, we're going to convert back and use the original velocity formula that we discussed all the way back from chapter 2. So V equals D over T. So if you plug in 91.4 and you divide that by 0.271, because that's distance over time, you should get roughly about 337.27 meters per second. And that's about the right speed if we're talking about a sound wave or whatever that's traveling through the air. Here's another example. If I tell you that we have that same frequency, same distance, same time, I want to know what the wavelength is now. Well, we just found out what velocity was. We just discovered that was 337.27. If you take that and plug it into the formula here, velocity divided by frequency, you divide that by 192, you should get 1.76. And that's in meters for your wavelength. Okay, and then again, you can also solve for the period. So we have frequency, 1 divided by 192. You should get about 0.005, and that should be in seconds. Okay, so remember, period, that is the time it takes for one cycle to occur. So for one crest to reach the next part of that crest. So from crest to crest, it's not just the wavelength, but the time it takes to get there is the period. So there are some practice problems on page 934, 15 through 20. Again, you can stop the video now, or you can leave quite a bit of space and come back to that in just a few minutes. Third section, and this is the final section for chapter 14. This is wave behavior. So how do waves interact? There's two things. Well, there's four things. There's reflection and refraction that are the closest, and this is what we're going to go into detail a lot more about once we hit chapter 17 and 18. So if we're talking about reflection, if you look here at this first image, you have this red line. That's called the normal. Okay, that's just kind of perpendicular to your surface. And you have an angle or a ray that comes in. That's your incident ray. And it creates an angle of incidence. So it's from your ray to the normal. Once it hits that mirror or that surface and it's reflected at the exact same angle as what it came in at. Okay, so if this one on this side, if your incidence is 30 degrees, your reflection is 30 degrees. Okay, now in another situation, we have refraction. So we have air, maybe water down here. So you have an incidence ray that comes in at a specific angle. And once it hits that surface, it's going to bend either toward the normal or away from the normal. Okay, and which it does depends on what your objects are that it's moving into. So this is an example. Refraction is an example of why when you look into a glass of water, your straw looks like it's broken or bent. Okay. Another thing is interference. You have waves that can be combined. So if they are combined and they're both kind of moving along the same path, both have crests and then troughs, you're going to create a much bigger wave. But if you have it to where it's almost the opposite, you have a crest and a trough coming together, it's just like subtraction, so it's going to create a smaller wave. And then the last type is diffraction, so you have a barrier or an opening that a wave has to travel through or around, and it causes that wave to bend because of that opening or that barrier. And you can see the difference in a large barrier or a large opening and a small opening. And that's it for chapter 14.